In this problem, I wanted to determine the force in the spring over here with the spring constant of K. The beam has a length of L. W is the distributed load, and I have an EI that is constant. Okay. Now, again, this is a redundant loading, statically indeterminate. I'm going to have 4 unknowns. I have 3 over here at A, and then I have a force over here at the endpoint. So 4 unknowns. Okay, I only have 3 equations. So I'm going to need to use what we've been talking about with statically indeterminate beams. Okay, so what I'm going to actually do is I'm going to break it up into 2 pieces. One is the distributed load that causes a deflection downward, and then one is the force of the spring that causes a deflection upward. Okay, so the total deflection is going to be, again, the deflection of the beam minus the deflection due to the spring of the end of the beam. Okay, and that's going to equal the total deflection. So the total deflection, again, by definition of Hooke's law, is the force of the spring over the spring constant. Okay, looking up in the appendix C in your book, okay, the deflection due to distributed load of a cantilever beam of the endpoint is this, and the deflection of a point load at the end of the beam is this. Again, my load is the force of the spring, which is also related to the total deflection of the spring. Okay, so force of the spring shows up twice, but that's really the only unknown in this equation, so I just use algebra to solve it. So rearranging things, bringing the force of the spring all to one side, getting rid of my denominator, I get an equation that looks like this, and then I can solve for the force of the spring to get that. So again, I break my system up into simpler parts that I can look up in the back of the book. And then using the deflection and what I know about the deflection and how it relates to the deflection of the spring, I can actually calculate the force of the spring using this superposition method.